If the idea that Earth's magnetic shield is weakening, splitting, and accelerating in ways no model predicted has you as unsettled as it has me, make sure you hit like and subscribe to Signal Watch so you don't miss a single update as this story develops. Drop a comment with where you're watching from, because depending on where you live, this story hits very differently. And tell me, do you think institutions are being straight with us about what the magnetic field data actually shows? If you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You are the reason we can keep chasing stories like this, so thank you for having our back. Now, here is what this investigation covers. A weak spot the size of a continent that is splitting in two, and what the instruments inside it are recording that the mainstream press is not talking about. A magnetic pole that has been sprinting toward Siberia at speeds that broke every model we had, and what that sprint tells us about the state of the liquid iron 3,000 kilometers beneath your feet. The last time the field did something like this, it took anywhere from 1,000 to 10,000 years to complete, and the geological record of what happened to life on the surface is not reassuring. And the satellites, the power grids, the navigation systems, and the migratory species that are all showing the same signal, and what that convergence means for the infrastructure of modern civilization. Now, settle in and let's get into it. There is a force surrounding this planet that you have never seen, never felt, and almost certainly never thought about today. You cannot touch it, you cannot smell it. On a clear afternoon, standing in a field, there is no sensory experience that would tell you it exists. And yet without it, you would not exist. Nothing complex would. The magnetic field, the magnetosphere, is the reason Earth has an atmosphere thick enough to breathe, oceans liquid enough to swim in, and a surface shielded well enough from the sun's radiation that biology had 4 billion years to figure out how to become us. That field is generated roughly 3,000 kilometers beneath your feet. At that depth, the outer core of the planet is not rock. It is liquid iron, a churning, convecting ocean of molten metal at temperatures exceeding 5,000 degrees Fahrenheit, driven by the heat bleeding out from the solid inner core below it. As that liquid iron moves, it carries electrical charges. Moving electrical charges produce magnetic fields. The result, amplified by the rotation of the planet itself into a self-sustaining dynamo, is the invisible shield that has been deflecting the solar wind, the constant stream of charged particles pouring off the sun, for billions of years. The solar wind is not a gentle breeze. It is a continuous bombardment of protons and electrons, traveling at speeds between 200 and 900 kilometers per second, carrying with it enough energy that, if the magnetic field were not there to deflect it, it would do to Earth's atmosphere over geological time what it did to Mars's. Mars lost its magnetic dynamo approximately 4 billion years ago. Its atmosphere is now 1% of Earth's surface pressure. Its surface is a frozen, irradiated desert where liquid water cannot exist. That is the end state of a planet without a magnetic shield. That is what the field protects us from, and the field is weakening. Not dramatically, not suddenly, not in a way that makes headlines or interrupts news cycles, but systematically, measurably, and, the part that matters, acceleratingly. The first person to establish a global baseline measurement of the field's strength was Carl Friedrich Gauss, the German mathematician, in 1840. Gauss developed the mathematical framework for measuring the field's intensity in absolute units, deployed a network of magnetic observatories across Europe, and produced the first systematic global map of the field's strength. That measurement established a baseline against which everything that has happened since can be compared. Since 1840, the overall strength of Earth's magnetic field has declined by approximately 10%. Let that number sit for a moment, not in the way cable news deploys a dramatic pause, but because the arithmetic that follows it matters. 10% in 180 years. That is roughly 5.5 per year, which sounds trivially small until you ask, is the rate constant or is it changing? The European Space Agency's Swarm mission, a constellation of 3 satellites launched on November 22, 2013, designed specifically to measure the field's strength, direction, and rate of change with unprecedented precision, provides the answer. And the answer is that the decline is not uniform. Roughly 8% of that 10% total decline has occurred since 1970. In the last 50 years, the field has lost more strength than in the preceding 130 years of measurement. That is an acceleration, not a gentle drift, an acceleration. Dr. Mioara Mandea at the Centre National d'Études Spatiales has spent much of her career studying precisely this phenomenon, the rate of change of the rate of change of the field. What she and colleagues have documented is that the field is not just declining, it is declining faster than it was declining before. The technical term is secular acceleration, the second derivative of the field's temporal variation. It is the difference between a car slowing down and a car whose brakes are failing progressively. The position of the car changes, the speed of the car changes, but the thing that tells you whether you should be worried is the acceleration, and the acceleration is what the institutional communications tend not to emphasize. Dr. Kieran Beggan at the British Geological Survey, who leads the team responsible for the World Magnetic Model, the mathematical model that underpins navigation systems on every smartphone, every aircraft, and every submarine on the planet, has been direct about what the swarm data is showing. The field's behavior, he has noted publicly, is outside the range of variability the models were calibrated against. Not dangerously outside, not catastrophically outside, but measurably, verifiably outside the envelope. The magnetopause, the boundary where the solar wind's pressure is balanced by the magnetic field's resistance, normally sits at roughly 10 Earth radii on the sunward side of the planet. That is approximately 64,000 kilometers between the outermost edge of the field's protection and the surface of the Earth. During major solar storms, when the solar wind intensifies, that boundary compresses. Under current field strength, it can be pushed into 5 or 6 Earth radii. As the field weakens further, that compression under equivalent storms becomes more severe. The shield retreats. But here is where the story gets specific. Because the global average decline, 10%, accelerating, is not the most alarming data point. The most alarming data point is what is happening in one particular region of the planet where the field is not just weaker than average. It is less than half the planetary average, and it is growing. Picture Earth's magnetic field as a suit of armor surrounding the planet. Not a uniform suit. The field is stronger at the poles, weaker at the equator, shaped by the dynamo beneath, but broadly continuous. A protective layer that, while not impenetrable, stands between the surface and the radiation environment of space. Now imagine a section of that armor has been compromised. Not scratched, not dented. Compromised, thin to less than half its normal thickness, covering an area roughly the size of South America and growing. That is the South Atlantic anomaly, and it has been there for at least 4 centuries of observatory records, a persistent, slowly expanding region centered roughly over Brazil and the South Atlantic, where the magnetic field at the surface is dramatically, anomalously, measurably weaker than everywhere else on Earth. The numbers from SWARM are unambiguous. At the heart of the South Atlantic anomaly, the field strength measured at the surface is approximately 22,000 nanoteslas. The global average is approximately 45,000 nanoteslas. At the poles, the field reaches 60 to 70,000 nanoteslas. The anomaly is not a mild deviation. It is a region where the field is less than half of what it should be, a gap in the armor where the inner Van Allen radiation belt, which normally orbits at safely elevated altitudes, dips close enough to Earth's surface that it intersects low Earth orbit. Every satellite passing through it flies through a radiation environment unlike anything in the rest of the orbital envelope. The cause of the anomaly is not a mystery. It is a consequence of the structure of Earth's outer core in this region. At the core mantle boundary, the interface between the liquid iron outer core and the solid rock mantle, roughly 3,000 kilometers beneath the surface, there exists, beneath South America and the South Atlantic, a region of reversed magnetic flux. The dominant magnetic field of Earth's dynamo points in one direction. This patch points in the opposite direction. The two cancel each other out, and the surface expression of that cancellation is the anomaly. Dr. Philip Livermore at the University of Leeds, one of the world's foremost authorities on core mantle boundary dynamics, has modeled this structure in detail. The reverse flux patch is not a static feature. It is driven by the flow of liquid iron in the outer core, and the evidence from SWARM suggests it is growing. Dr. Fernando Jorge Sousa Pais, also at Leeds, has published modeling showing that the anomaly has been drifting westward at approximately 0.3 degrees per year, consistent with the westward flow of liquid iron at the outer core surface. The anomaly is not fixed. It moves. It evolves. And in the last decade, it has done something that no observatory record going back 4 centuries had captured before. It has split. Beginning around 2015 to 2016, data from the SWARM satellites began showing the emergence of a second intensity minimum within the South Atlantic anomaly, a second lobe of anomalously weak field developing off the southwestern coast of Africa, separate from the original center over Brazil. By 2020, the split was unambiguous enough that Pavon Carrasco and DeSantis published a landmark paper in Frontiers in Earth Science, documenting it explicitly and asking the question that its title made unavoidable: whether the split represented a key indicator of an approaching geomagnetic reversal. The two-lobe structure is not random. It is a specific signature. When you look at the paleomagnetic record, the history of the field locked into ancient volcanic rock and ocean sediment going back millions of years, a multi-lobe structure in the anomaly region appears in the records immediately before geomagnetic excursions and reversals. The field becomes multipolar rather than dipolar. The single dominant north-south axis begins to fragment. Multiple magnetic poles appear. The armor doesn't just thin, it starts to come apart in pieces. The SWARM data shows this process beginning. Not completed, not irreversible, but beginning. And the split has deepened with each successive year of satellite measurement since 2016. There is another dimension to this that the headline numbers do not capture. The anomaly is not just weak. It is weak in a location that happens to sit directly beneath the orbital corridor used by every low Earth orbit spacecraft, operated by every space agency and commercial operator on the planet. The International Space Station passes through it. The Hubble Space Telescope passes through it. Every Starlink satellite passes through it with every orbit. This is not an abstraction. It is an operational reality that every satellite operator on Earth has to plan around, and the planning requirements are getting more demanding every year. The Hubble Space Telescope has been in orbit since April 24, 1990. In 35 years of operation, it has produced images that redefined cosmology, measured the expansion rate of the universe, and captured phenomena no ground-based instrument could see. It is arguably the most scientifically productive spacecraft in human history. And on every single pass through the South Atlantic anomaly, Hubble automatically shuts down its scientific instruments. Not because of a malfunction, not as a precaution against a rare event. As a standard, automatic, non-negotiable operational protocol. Because the radiation environment inside the anomaly is sufficiently hostile that the instruments cannot be trusted to return reliable data, and the energetic proton hits are sufficiently frequent and damaging that extended instrument exposure would accumulate degradation that shortens the telescope's operational lifetime. Approximately 10% of Hubble's orbital passes intersect the anomaly. That is 10% of every orbit, every day, every year for 35 years, during which the observatory is effectively blind and absorbing damage. Over its operational lifetime, Hubble has experienced more than 100,000 documented hits from energetic protons during SAA transits, enough to measurably degrade detector performance in ways that the engineering teams at NASA Goddard Space Flight Center have had to compensate for in the data processing pipeline. The detectors work around the damage, but the damage is real, it is cumulative, and it is specifically attributable to the anomaly. The International Space Station presents a different kind of data. The station carries dosimetry instruments throughout its pressurized modules, radiation monitors that track the exposure received by crew members during their missions. The South Atlantic anomaly contributes an estimated 15 to 20% of the total annual radiation dose received by ISS crew, according to NASA's Human Research Program data. On days of elevated SAA activity, which correlates with the field's continued weakening in the region, crew members can receive close to 1 additional millisievert per day from SAA transits alone. For context, 1 millisievert is approximately the dose received from 5 conventional chest X-rays. Japan's Akabono satellite, which operated in a low elliptical orbit that repeatedly intersected the anomaly, documented memory upset events, instances where high-energy particle hits flipped binary states in onboard computer memory at a rate 5 times higher inside the SAA than in the rest of its orbital path. Memory upsets are recoverable in most cases, but they interrupt operations, require error correction, and in worst-case scenarios can corrupt critical command sequences. The satellite kept flying, but the anomaly's fingerprint on its operational record was unmistakable. The Landsat 7 and 8 Earth observation satellites, operated by NASA and the U.S. Geological Survey, imaging every point on Earth's surface on a 16-day repeat cycle. Both carry special radiation shielding designed specifically for SAA transit protection. The design requirement exists because without it, the elevated particle flux inside the anomaly would produce single-event upsets in the onboard computer systems at rates that would compromise the imaging data. The shielding adds mass. Mass costs money. The South Atlantic anomaly is expensive in ways that never appear in any single budget line, but accumulate across every mission designed to orbit Earth. And here's the number that closes the loop on where the trend is heading. Analysis of satellite anomaly databases. Systematic records of anomalous events logged by operational satellites across multiple fleets shows that the rate of SAA attributable upsets increased by approximately 30% between 2005 and 2020. 30% in 15 years. Consistent with, and when plotted against the swarm measurements, directly correlating with the continued weakening of the field inside the anomaly during that same period. The anomaly is getting worse. The satellites are logging the proof of that every day. Dr. James Birch at the Southwest Research Institute, who served as principal investigator for NASA's Van Allen probes mission, has emphasized that the radiation belt dynamics inside the SAA are not static. The inner belts dip toward Earth's surface in this region is a direct consequence of the field's weakness there. And as the field continues to weaken, the dip deepens. Dr. Srikanth Kanikal at NASA Goddard has published extensively on how the belt structure responds to field variations on both short and long timescales. The trajectory, as the field in the SAA continues its measured decline, is not ambiguous. Now, the satellites are the visible casualties. They are the systems sophisticated enough to log their own damage and report it to engineers on the ground. But there is another story happening simultaneously, and it is happening at the opposite end of the planet. While the SAA expands and deepens over the South Atlantic, the magnetic North Pole has been doing something that no instrument ever recorded before. Something that forced the agencies responsible for global navigation to break their own update schedule in an emergency that most of the world never heard about. The magnetic North Pole is not where your compass points on a map of the Arctic. It is the point on Earth's surface where the magnetic field lines plunge vertically into the ground, where a compass held horizontally would spin uselessly because the field is pointing straight down. It wanders. It has always wandered. For most of recorded history, that wandering was slow enough that the World Magnetic Model, the mathematical framework maintained jointly by NOAA and the British Geological Survey that converts the field's behavior into navigational corrections, could be updated on a comfortable 5-year cycle and remain accurate enough for every navigational system that depended on it. In 1900, the magnetic North Pole sat at approximately 81 degrees north, 110 degrees west, in the Canadian Arctic, northwest of Hudson Bay. Through the 20th century, it drifted slowly toward the geographic pole and then began a gradual turn toward Siberia. The average drift rate through most of the 20th century was roughly 0 to 15 kilometers per year. Slow, predictable, manageable. Then, sometime around the turn of the millennium, something changed in the outer core beneath Canada and Siberia. The drift began accelerating, not immediately to alarming speeds, but measurably faster than the century-long baseline. By 2017, the pole was moving at more than 50 kilometers per year. By 2019, it had crossed the international dateline into the Eastern Hemisphere, moving from the Canadian side of the Arctic to the Siberian side for the first time in any instrumental or historical record. As of 2024, the pole sits at approximately 86.5 degrees north, 162 degrees east. It is moving at over 90 kilometers per year. To put that in perspective, the pole is now moving at roughly the speed of a brisk jog. Every single day, the point where Earth's field plunges vertically into the planet is approximately a quarter of a kilometer further than it was the day before. Every year, it shifts by a distance comparable to the length of a small city. And it is not slowing down. The World Magnetic Model's 5-year update cycle was designed around the historical drift rate. The 2015 edition of the model was validated and released with an expected operational lifespan through 2020. The model works by fitting a mathematical description of the field to the latest measurement data, projecting forward, and generating the correction tables that navigation systems apply to translate magnetic compass readings into true geographic bearings. As long as the field behaves within the range the projection assumes, the model stays accurate. In 2018, the pole's acceleration had pushed the model's error in some high-latitude regions to within a fraction of a degree of the tolerance threshold, the point at which the mathematical description no longer matched reality closely enough to be trusted for operational navigation. That threshold was supposed to be safely in the future. The 2015 model was supposed to last until 2020. It didn't. On February 4th, 2019, NOAA and the British Geological Survey released an emergency out-of-cycle update to the World Magnetic Model, 1 full year ahead of schedule. The official joint statement identified the pole's unpredicted acceleration as the trigger. Dr. Kieran Begin, BGS's lead on the WMM, confirmed publicly that the rate of polar movement had simply exceeded what the 2015 model's projection had anticipated. The model was updated, the navigation tables were revised, and the world's navigational infrastructure quietly recalibrated itself around a new mathematical description of a pole that had moved to a place no model had predicted it would be. The cause of the acceleration was identified, insofar as any single cause can be isolated in the chaotic dynamics of a liquid iron ocean, in a paper published in Nature Geoscience in 2017. Dr. Philip Livermore and colleagues at the University of Leeds described a high-speed jet of liquid iron flowing at the boundary of the outer core, roughly 3,000 kilometers beneath Canada and Siberia. This jet, moving at speeds of approximately 50 kilometers per year relative to the surrounding core material, making it the fastest known flow in Earth's interior, is the mechanical driver of the pole's acceleration. As it flows, it carries and concentrates magnetic flux in ways that shift the location where the field's lines converge at the surface. The pole follows the flux follows the jet, and the jet, as of the most recent analyses, shows no signs of decelerating. But a sprinting pole and an expanding wound in the field are not two separate stories. As the swarm satellites reveal, they are two symptoms of the same underlying process, and that process has a name in the geological record, a name that carries very specific, very well-documented implications for what comes next. There is a library buried in the ocean floor, not a metaphor, a literal archive of Earth's magnetic history, written in iron-bearing minerals and preserved in rock that has been accumulating for hundreds of millions of years. When volcanic rock cools through a temperature called the Curie point, approximately 580 degrees Celsius for the mineral magnetite, the magnetic domains within it lock into alignment with whatever direction and intensity the field happens to be pointing at that moment. The rock solidifies. The field signature is frozen into it, and it stays frozen, undisturbed, for as long as the rock remains unmelted and unweathered. At the mid-ocean ridges, the underwater mountain ranges where tectonic plates pull apart and new seafloors continuously created from upwelling magma. This process has been running like a tape recorder for tens of millions of years. New rock forms at the ridge center, cools, locks in the field direction, and is carried outward on both sides as the plates spread. The result is a series of parallel magnetic stripes on the ocean floor, alternating between rocks that locked in a field pointing roughly north, like today, and rocks that locked in a field pointing roughly south. Each stripe is a reversal. Each boundary between stripes is a moment when the field flipped. Scientists can read that tape. They have been reading it since the 1960s, when the discovery of the seafloor spreading record provided the first direct confirmation of both plate tectonics and geomagnetic reversals. What the tape shows is a system that has reversed its polarity more than 180 times in the last 83 million years. Not smoothly, not on a clock schedule, but repeatedly, sometimes separated by tens of millions of years of stable polarity, sometimes flipping in rapid succession every few 100,000 years. The last full reversal, the Brunhes-Matuyama boundary, occurred approximately 780,000 years ago. Before that reversal, Earth's field pointed south. After it, the field pointed north. That is the polarity we live in today. And when you calculate the average interval between reversals over the last 83 million years, you get a number of approximately 450,000 years. We are now approximately 780,000 years into the current polarity. We are, by the long-term statistical average, roughly 1.7 times overdue for a reversal. That number alone means very little. Reversals are not clockwork. The interval between them is not a timer counting down. The field has gone longer than 780,000 years between reversals before and then reversed. It has also reversed rapidly in succession. Statistical overdue is a weak signal. What is a much stronger signal is the pattern of what happens to the field in the centuries and millennia immediately before a reversal. And those patterns are now preserved with enough fidelity in the paleomagnetic record that scientists can identify specific signatures. Dr. Jean-Pierre Vallée at the Institut de Physique du Globe de Paris has spent decades extracting reversal precursor signatures from high-resolution sedimentary records, deep-sea sediments that, unlike the volcanic ocean floor stripes, preserve a continuous temporal record of the field's behavior rather than a frozen snapshot. What Vallée and colleagues have found is that reversals are typically preceded by a characteristic decline phase. The overall dipole strength falls, sometimes gradually, sometimes more sharply, before the field enters a transitional period of multipolar, complex behavior, and ultimately restabilizes in the opposite polarity. The decline to reversal threshold is not instant. It unfolds over centuries to millennia. The threshold the data points to, the dipole moment below which previous reversals have initiated, is approximately 4 times 10 to the 22nd ampere meter squared. That is a specific number, and it matters. Earth's current dipole moment, as measured by SWARM in 2023, is approximately 8 times 10 to the 22nd ampere meter squared. We are at roughly twice the reversal initiation threshold. The field has declined by 10% since 1840, and that decline has been accelerating. But the current moment is still comfortably above the threshold values associated with previous reversals, comfortably above with an accelerating decline rate. Dr. Kathy Constable at the Scripps Institution of Oceanography, who has worked extensively on long-term field behavior modeling, notes that the current field state is unusual, not just in the rate of decline, but in the combination of features, the rapid pole motion, the SAA growth and splitting, the overall dipole weakening occurring simultaneously. Each feature has occurred before in the geological record. The combination of all of them together at the same time is the pattern that precedes excursions and reversals. Dr. Andrew Roberts at the Australian National University, whose work on high-resolution sedimentary paleomagnetic records has refined the timeline of past field events, has emphasized the importance of the SAA's two-lobe structure in this context. In the records from the period immediately preceding previous geomagnetic excursions, near reversals from which the field recovered without completing a polarity flip. A multi-lobe anomaly structure appears in the South Atlantic region. The field becomes locally multipolar. Multiple centers of weakness emerge. The armor develops multiple thin spots simultaneously. What the swarm data is now showing in real time is that structural signature beginning to form. The geological record tells us what the field has done before. It cannot tell us, at least not with the resolution we would want, what happens to life on the surface during those events. For that, we have to look at a different kind of archive, one that is 41,000 years old, and one that produced a signal so strong it left its mark in ice cores on both poles simultaneously. 41,000 years ago, the field nearly reversed. Not a full flip. The polarity did not permanently switch from north to south, but for a period lasting roughly 1,000 years at its minimum, and spanning a broader excursion window of approximately 4,500 years, the field collapsed to approximately 4 to 5% of its current strength. The magnetic poles wandered to the equatorial region. The field became multipolar and chaotic, not one north pole and one south pole, but a complex shifting pattern of poles scattered across the planet's surface. The magnetospheric shield that normally stands between the surface and the radiation environment of space was, for all practical purposes, gone. This event is called the Lachant excursion. It is the best studied geomagnetic near reversal in the record, partly because its timing falls within the range of carbon-14 dating and other high-resolution chronological methods, and partly because the signal it left in the geological record is so strong that it appears in ice cores, deep sea sediments, and volcanic rocks on every continent. The most direct measurement of what the Lachant minimum meant for the radiation environment comes from cosmogenic isotopes. When cosmic rays, high-energy particles from outside the solar system, strike the upper atmosphere, they produce distinctive isotopes: beryllium-10 from nitrogen and oxygen, chlorine-36 from argon. These isotopes rain down on the surface and are preserved in ice sheets and sediments. The higher the cosmic ray flux reaching the atmosphere, the more isotopes are produced. The isotopes are a dosimeter for the radiation environment, preserved in ice that has been accumulating for hundreds of thousands of years. Dr. Raymond Muschler at Lund University has extracted the Lachant signal from ice core beryllium-10 records with extraordinary precision. At the Lachant minimum, beryllium-10 production increased by approximately 180% above background levels. 180%. That is not a marginal increase. That is nearly 3 times the normal cosmic ray production rate, sustained for centuries, preserved in ice on both Greenland and Antarctica. Chlorine-36 records independently confirm the spike. 2 different isotopes, 2 different poles, 1 signal. The field fell, the cosmic rays flooded in, and the atmosphere recorded the flood in chemistry that is still readable today. Now connect that radiation environment to the biological record of the same period. This requires care. Correlation is not causation, and the Lachant period overlaps with other significant changes, including climate shifts and the migration of anatomically modern humans. But a paper published in Science in 2021 by Dr. Alan Cooper of the University of Adelaide and Dr. Chris Turney of the University of New South Wales, along with a large collaborative team, made the connection with a rigor that has not been seriously challenged since. Cooper and Turney analyzed ancient DNA extracted from permafrost specimens of megafauna, the large mammals that dominated the landscapes of Australia, the Americas, and Eurasia in the late Pleistocene. They found that population crashes and extinctions clustering in the 40 to 42,000 year window, squarely within the Lachant excursion, were consistent across multiple species on multiple continents. The mechanism they proposed was not direct radiation exposure. Animals are not particularly sensitive to the radiation levels involved. The mechanism was the food chain. Elevated UVB radiation, the consequence of ozone depletion driven by the increased cosmic ray and solar particle flux during the field minimum, would have stressed plant communities and reduced primary productivity across large areas. Animals that depended on those plant communities faced resource crashes. The Neanderthal extinction falls within this window. The latest confirmed Neanderthal fossil remains date to approximately 40,000 years ago, a figure established by Thomas Hyam and colleagues in a comprehensive redating study published in Nature in 2014. Neanderthals had survived for at least 300,000 years through ice ages, climate shifts, and competition with other hominin species. They disappeared within the Lachamp window. That may be coincidence. It may be the compound effect of multiple simultaneous pressures: the field minimum, climate change, competition with modern humans. The honest answer is that the data cannot yet disentangle the factors with certainty, but the timing is not comfortable to dismiss. And this is where the story takes a turn that most people haven't heard about, because the Lachamp excursion also left an imprint on the sky. Dr. Monika Korda at the GFZ German Research Center for Geosciences has modeled the auroral environment during the Lachamp minimum. Under normal field conditions, the aurora, the visible glow produced when charged solar particles follow field lines into the upper atmosphere, is confined to the polar regions. During Lachamp, with the field collapsed to 5% of its current strength and the magnetic poles wandering to equatorial latitudes, the auroral oval would have expanded to within approximately 15 degrees of the equator. The aurora would have been visible from Brazil, from Central Africa, from Southeast Asia. The sky would have been lit on a regular basis by curtains of light that no human alive today has ever seen at those latitudes. That was 41,000 years ago. A world without satellites, without power grids, without a global navigation system that every ship, every aircraft, and every smartphone on the planet depends on. The Lachamp minimum was a disaster for the Pleistocene megafauna and possibly for the Neanderthals. But the world it happened to was biological. The world a comparable event would happen to now is technological. And the audit of technological vulnerability begins with the systems we have placed directly inside the region where the field is already weakest. As of early 2025, there are approximately 10,000 active satellites in orbit around Earth. 10,000. That number was under 2,000 as recently as 2019. The explosion of commercial satellite constellations, led by SpaceX's Starlink, which had approximately 6,500 active satellites in January 2025 with authorization for up to 42,000, has transformed low Earth orbit from a sparsely populated scientific and governmental domain into what is effectively an industrial zone, humming with commercial infrastructure that hundreds of millions of people depend on for internet access, weather forecasting, financial transactions, and navigation. Every single one of those satellites passes through the South Atlantic anomaly with every orbit. Low Earth orbit is typically defined as altitudes between roughly 160 and 2,000 kilometers above the surface. The International Space Station orbits at approximately 400 kilometers. Most of the Starlink constellation operates between 540 and 570 kilometers. This altitude range is precisely where the inner Van Allen radiation belt's anomalous dip into the SAA produces the most severe radiation environment. The protons that damage satellite electronics, energies in the tens to hundreds of mega electron volts, are densest in the belt's inner region, and in the SAA, that region reaches down to where the satellites live. The numbers that define the hazard are stark. Inside the SAA, at typical LEO altitudes, single event upset rates, instances where a high-energy particle flips a bit in onboard computer memory, run approximately 100 to 1,000 times higher than in the magnetically protected regions of the same orbital shells, according to data published in IEEE transactions on nuclear science. Total ionizing dose at 400 kilometers altitude inside the SAA runs approximately 100 milligray per year for unshielded components. In the benign orbital regions outside the anomaly at the same altitude, the figure is 5 to 10 milligray per year. The SAA is not a slightly elevated radiation environment. It is a qualitatively different radiation environment. Now apply those numbers to a field that is continuing to weaken. Dr. Uri Spritz at the GFZ German Research Center for Geosciences and UCLA has modeled the consequences of progressive field reduction on the inner Van Allen belt structure. His modeling shows that at 50% of the current field strength, a level the current decline rate, if sustained, would reach within a few centuries. The inner belt's cross-sectional area expands to approximately 3 times its current size. 3 times the area means 3 times as much of low Earth orbit is enveloped in the inner belt's radiation environment. The SAA, instead of being a specific hazardous zone that satellites pass through on their orbital tracks, becomes the dominant radiation environment for the entire low Earth orbit shell. Satellites are designed and tested against the radiation environment they are expected to encounter during their operational lifetimes. Those specifications are derived from models of the current radiation belt structure under current field conditions. They are not designed for a field at 50% strength. They are not designed for an inner belt 3 times its current size. The testing and certification infrastructure for satellite electronics, the radiation hardness specifications, the total ionizing dose requirements, the single event latch-up thresholds was developed during a period of magnetic stability that the current trajectory of the field is moving away from. Dr. Daniel Baker at the University of Colorado's Laboratory for Atmospheric and Space Physics, one of the world's leading authorities on radiation belt dynamics, and what he has called the killer electrons of the outer belt, has been direct about the vulnerability of the current satellite infrastructure to elevated radiation environments. The commercial constellations being deployed now, Starlink, OneWeb, Amazon's Project Kuiper, were designed for the radiation environment that existed when they were designed. They were not designed for a progressively degrading magnetic shield. Dr. Sébastien Borderie at ONERA, the French aerospace laboratory that maintains some of the most sophisticated particle flux models for satellite operations, has modeled the SAA's particle flux evolution in conjunction with swarm field measurements. The trend in the data is consistent across models. As the field in the SAA region continues to weaken, the proton flux at LEO altitudes inside the anomaly increases. Not catastrophically, not on a year-by-year basis that would be immediately operationally alarming, but on the decade-to-century timescale that defines the investment horizon for satellite constellation infrastructure, the trajectory is significant. The GPS constellation orbits much higher, at approximately 20,200 kilometers in medium Earth orbit. At this altitude, the inner belt's direct effects are less severe, but the outer radiation belt is more relevant. Dr. Spritz's modeling suggests that at 50% field strength, total ionizing dose rates at GPS altitudes would increase by an estimated factor of 2 to 3. GPS satellites have operational lifetimes of approximately 15 years. The investment cycle for replacing and upgrading the constellation means that decisions being made today about GPS satellite specifications and shielding will determine the constellation's resilience to a radiation environment that the field's current trajectory is moving toward. But the satellites are the most visible vulnerability. They are the one vulnerability that engineers know about and have at least partially prepared for, with shielding specifications, anomaly protocols, and operational procedures that acknowledge the SAA's hazards. The vulnerability that has received almost no serious attention, the one that involves the largest single piece of infrastructure humanity has ever built, is not in space. It is on the ground, and the mechanism that connects the field's behavior to that infrastructure runs through the physics of what happens when a changing magnetic field encounters a long conductor. On September 1st and 2nd, 1859, the largest solar storm in the historical record struck Earth's magnetic field. The Carrington event, named for the British astronomer Richard Carrington, who observed the associated solar flare, compressed the magnetosphere dramatically, drove a global geomagnetic storm of extraordinary intensity, and induced electrical currents in the telegraph networks of North America and Europe that were powerful enough to set telegraph offices on fire. Operators reported receiving electrical shocks from their equipment. In some locations, telegraph systems continued operating after being disconnected from their power supplies, running entirely on the current induced by the geomagnetic storm. The auroras were visible in Cuba, in the Bahamas, in Colombia. In the Rocky Mountains, the light was bright enough to wake gold miners who thought it was morning. Lloyd's of London conducted an analysis in 2013 of what a Carrington scale event would cost in the modern context. Their estimate, $2 to $10 trillion in economic damage to the North American electric grid alone. For context, the entire GDP of Germany, the fourth largest economy in the world, is approximately $4 trillion. The mechanism that converts a geomagnetic storm into infrastructure damage is called geomagnetically induced currents. When the magnetic field changes rapidly, as it does during a storm, when the solar wind's pressure drives rapid variations in the field's configuration, those variations induce electrical currents in any long ground-based conductor. Faraday's law of electromagnetic induction, a changing magnetic flux through a conductor induces a voltage. The longer the conductor, the larger the induced voltage. High-voltage transmission lines stretch for hundreds of kilometers, pipelines stretch for thousands, and the infrastructure most critically vulnerable, the extra high-voltage transformers that sit at the nodes of the transmission grid and step voltages up and down for long-distance power transmission, are designed to handle alternating current at 60 Hz. The geomagnetically induced currents that storms drive into them are quasi-direct current, essentially zero-frequency DC, injected into a system built exclusively for AC. The result is transformer saturation, overheating, and in severe cases, catastrophic physical damage. The Quebec blackout of March 13, 1989, is the calibration point for modern grid vulnerability. A geomagnetic storm reaching a KP index of 9, significant but far below Carrington level intensity, collapsed the entire Hydro-Quebec transmission system in 90 seconds. 6 million people lost power for up to 9 hours. The damage, primarily to transmission equipment, cost an estimated $200 million. More alarming than the cost was the speed. The grid did not degrade gradually. It failed catastrophically and nearly instantaneously once the induced current thresholds were exceeded. Now, introduce the magnetic field's weakening into this calculation. Dr. Antti Pulkkinen, formerly at NASA Goddard and subsequently at the University of Maryland, published analysis in Space Weather Journal in 2017, establishing the relationship between ambient field strength and GIC magnitude. The core finding, for the same solar storm input, the same level of solar wind pressure, the same storm intensity, geomagnetically induced currents in ground conductors increase as the ambient magnetic field weakens. A field at 50% of its current strength, hit by a storm equivalent to the 1989 Quebec event, would produce GICs approximately twice as large as those that collapsed the Hydro-Quebec system in 90 seconds. Twice as large. The Quebec blackout was not a Carrington event. It was a moderate geomagnetic storm that happened to hit a grid at a geometrically vulnerable moment. The physical damage was recoverable within hours, but the infrastructure of today's grid is categorically more vulnerable than the grid of 1989. More interconnected, higher voltage, more dependent on the continuous operation of a smaller number of very large, very specialized transformers. And the most critical vulnerability in that infrastructure is the extra high voltage transformer. These units, the largest of which weigh between 100 and 400 tons, are custom manufactured for specific grid locations. They cannot be ordered off a shelf. Their lead time, from order to delivery and installation, is 12 to 18 months under normal manufacturing conditions, and can stretch to 3 years if multiple units are damaged simultaneously and the manufacturing capacity is saturated. The United States Department of Energy's own analysis, published in the Large Power Transformer Study of 2014, established that the United States has fewer than 2,000 of these critical units in its entire grid and maintains essentially no strategic reserve. Dr. James Gilbert, who testified before Congress on grid vulnerability to geomagnetic and electromagnetic pulse events, described the transformer inventory as one of the most critical and underappreciated vulnerabilities in American infrastructure. One transformer. 12 to 18 months to replace. Damage by a storm that the weakening field makes more damaging. That is the arithmetic of grid vulnerability under a progressively weakened magnetic shield, and there is a connection here that closes a loop opened earlier in this investigation. Dr. Livermore's high-speed jet of liquid iron beneath Canada, the same jet that is driving the magnetic North Pole's unprecedented sprint towards Siberia, also influences the rate of variation of the field in the high-latitude regions of North America. The field variation rate during storms in these regions is partly a function of the core dynamics driving the jet. The same process that is accelerating the pole is the process that shapes the field's behavior during storms in the zone directly above the most geomagnetically exposed portion of the North American power grid. The pole is sprinting, the SAA is splitting, the field is weakening, and the grid sits underneath all of it, built to tolerances calibrated against a magnetic environment that is no longer what it was when those tolerances were set. But there is one more system affected by the field's behavior, and unlike the satellites in the grid, it was not designed by engineers and cannot be upgraded with a software patch. It is the biological system, and the signal from the natural world is, in some ways, the most unambiguous data in this entire investigation. There is a sea turtle alive somewhere in the Atlantic Ocean right now that knows where it was born. Not approximately, not roughly. It knows the specific stretch of beach, the specific magnetic signature of that beach, encoded in the field's local intensity and inclination angle at that precise location, that it emerged from as a hatchling decades ago. When it is ready to nest, it will navigate thousands of kilometers of open ocean, with no landmarks, no visible stars on cloudy nights, no trail to follow, and arrive at a beach within kilometers of where it hatched. The precision is not metaphorical. It is measurable. It has been measured. Dr. Kenneth Lohman at the University of North Carolina at Chapel Hill has spent more than 2 decades documenting the mechanism behind this navigation. Loggerhead sea turtles imprint on the magnetic field signature of their natal beach, the specific combination of field inclination and intensity that is unique to that location, and use it as a navigational target for the rest of their lives. In laboratory experiments, Lohman and colleagues exposed hatchling turtles to the magnetic signatures of beaches hundreds of kilometers from their natal beach. The turtles oriented toward the direction that would, in the open ocean, have taken them to the location with that magnetic signature. They were not following a smell or a current or a star. They were reading the field. That mechanism, magnetoreception, is not unique to sea turtles. It is one of the most widespread sensory systems in the animal kingdom. Migratory birds use it. Honeybees use it. Salmon use it to return to their birth rivers after years in the open ocean. Monarch butterflies use it. Dr. Stephen Reppert at the University of Massachusetts Medical School demonstrated in work published in Nature Communications in 2014 that monarch butterflies carry a magnetic compass that they use in conjunction with their solar compass, a backup navigation system built into an insect that weighs less than half a gram. Dr. Henrik Moritzen at the University of Oldenburg has produced some of the most precise work on migratory bird magnetoreception, showing that European robins can detect magnetic field variations as small as 50 nanoteslas, variations smaller than the daily fluctuation of the field during mild space weather events. 50 nanoteslas. The field in the South Atlantic anomaly is approximately 23,000 nanoteslas below the global average. The gradient across the anomaly's boundary, the rate of change of field strength as you move into or out of the anomaly, is measurable over distances of hundreds of kilometers. For a migratory bird flying across the South Atlantic, crossing into the anomaly is not a subtle perturbation. It is an abrupt, significant shift in the magnetic environment that the bird's sensory system evolved to read as a navigational reference. The consequences are beginning to show in the biological record. The Tamar Project, Brazil's federal sea turtle conservation program, which has been monitoring nesting beaches along the South American coast for decades, has documented elevated rates of disoriented hatchlings and anomalous stranding events in coastal zones that overlap with the SAA's footprint. The correlation is preliminary, and the Tomar researchers are appropriately cautious about causal claims. But the geographic pattern, disorientation clustering in SAA proximate regions, is consistent with what Lohmann's laboratory work predicts. The whale strandings data is more statistically robust. A study published in Current Biology in 2020 by Granger and colleagues analyzed 14 years of stranding records from the International Whaling Commission database and found that gray whale strandings increased significantly on days of elevated solar radio flux, a proxy for geomagnetic disturbance, compared to geomagnetically quiet days. The effect was not marginal. The stranding rate on disturbed days was measurably and significantly higher than on quiet days across the full 14-year dataset. The proposed mechanism is magnetoreception disruption. Whales, like turtles, appear to use the magnetic field as a navigational reference in open water, and geomagnetic disturbances, which produce rapid, irregular variations in the field's direction and intensity, apparently degrade that reference badly enough that whales make navigational errors that drive them into shallow water. Now scale that disruption to the current trajectory of the field. The South Atlantic anomaly is expanding. The pole is moving at 90 kilometers per year. The overall field strength is declining. For every species that uses the magnetic field as a navigational reference, and there are dozens of them across every major taxonomic group of animals, the map is changing. Not in the sudden temporary way that a geomagnetic storm changes it. Permanently, continuously, in the same direction every year. The magnetic map that a loggerhead turtle imprints on as a hatchling is not the same map that existed when its mother hatched. The declination corrections that a European robin's ancestors evolved to navigate by are not the corrections that work today. The pole is moving faster than any previous generation of these animals has ever experienced. Faster, almost certainly, than the multi-generational timescale over which migration routes and magnetic imprinting behaviors are inherited and refined through natural selection. Dr. Moritzen has been explicit about this concern in interviews and in published work. The rate of magnetic change that migratory birds are now experiencing exceeds what evolutionary biology can reasonably be expected to track. Adaptation takes generations. The pole is moving 90 kilometers per year. The gap between what the field is doing and what the nervous systems of migratory species evolve to handle is widening every year. And if the biological navigation systems are already showing measurable stress under the field's current rate of change, before any excursion, before any reversal, before the field reaches anything close to the Lachamp minimum, the question of what a genuine field collapse would do to those systems is not an abstract one. It is a question with an answer in the geological record, and that answer connects to a chain of consequences that does not stop at disoriented turtles and stranded whales. It runs all the way to the bottom of the ocean food web and back up through every trophic level that 7 billion humans depend on. The solar wind is the threat that most people think of when they think about the magnetic field's protective role. Charged particles from the sun deflected by the magnetosphere. That is accurate as far as it goes. But the solar wind is not the most energetic radiation that the magnetic field shields against. The most energetic particles in the near-Earth radiation environment come from much further away. From supernovae, from neutron star mergers, from the violent processes at the centers of distant galaxies. They are called galactic cosmic rays, and they arrive continuously from all directions at energies so high that the Earth's magnetic field can only partially attenuate them even at full strength. At full strength. The key phrase. The magnetic field's ability to deflect a charged particle depends on the particle's energy relative to the field's rigidity, essentially how strong the field is. Low-energy particles are deflected efficiently. High-energy galactic cosmic rays are only partially deflected even by the full-strength field. As the field weakens, the cutoff rigidity, the energy threshold below which particles are deflected, decreases. More particles get through, more particles reach the upper atmosphere, more particles reach the surface. Dr. Ilya Usoskin at the University of Oulu has done some of the most precise quantitative work on this relationship. His analysis establishes that for each 10% reduction in the dipole moment strength, cosmic ray flux at Earth's surface increases by approximately 3 to 4%. Apply that to the current situation. The field has declined by 10% since 1840. The surface cosmic ray flux has already increased by an estimated 3 to 4% as a consequence of that decline. Not dramatically, not enough to produce immediate health consequences for people at sea level, but measurably, verifiably, and trending in one direction. The ground-based neutron monitor network provides direct observational confirmation. Neutron monitors, instruments that detect the secondary particle showers produced when cosmic rays strike the upper atmosphere, have been operating continuously since the International Geophysical Year of 1957 and 1958. The stations at Oulu in Finland and McMurdo in Antarctica have among the longest continuous records. When you extract the cosmic ray trend from those records, correcting for the solar cycle's 11-year modulation of cosmic ray flux, a gradual long-term increase is present, consistent with and at the magnitude predicted by the field's measured decline. The most immediate practical consequence of the rising cosmic ray flux is not at the surface, it is at altitude. At cruising altitude for commercial aviation, approximately 35,000 feet, the atmosphere provides far less shielding than at the surface, and cosmic ray flux at that altitude is already approximately 100 times the surface background. Aircrew members who fly long-haul routes, particularly polar routes where the field's coverage is already thinnest, accumulate radiation doses that approach the limits recommended by the International Commission on Radiological Protection. The ICRP recommends that occupational radiation workers not exceed 20 millisieverts per year. Aircrew on high-frequency long-haul polar routes can accumulate 6 to 9 millisieverts per year from cosmic radiation alone. Not yet at the limit, but within a factor of 2 to 3 of it. And that factor is shrinking as the field continues its decline. Now project the cosmic ray flux forward to a Lachamp scale field minimum. At 5% of the current dipole strength, the relationship Uzoskin has quantified would predict a surface cosmic ray flux increase of a factor of 2 to 5 above current levels, 5 times the current cosmic ray flux at Earth's surface, 100 times the current cosmic ray flux at aviation cruising altitude. The implications for commercial aviation under those conditions. If aviation as we know it were even still operationally viable, given the simultaneous satellite and navigation disruptions, are not something any regulatory body has formally assessed. But the cosmic ray increase during a field minimum does not only affect satellites and aircrew. It reaches into the atmosphere itself, and what it does there involves chemistry that connects directly to the surface of the planet where crops grow, where phytoplankton photosynthesize, and where the food systems supporting complex life operate. Cosmic rays are a primary driver of certain stratospheric chemical reactions. When high-energy particles penetrate the stratosphere, they ionize nitrogen and oxygen molecules, producing nitrogen oxides, compounds that catalytically destroy ozone. The ozone layer is not just an atmospheric curiosity, it is the filter that blocks most of the sun's ultraviolet B radiation. The wavelengths most damaging to DNA, most harmful to photosynthetic organisms, and most capable of driving the kind of surface biological disruption that the Cooper et al. Paper in Science identified as the primary kill mechanism during the Lachamp excursion. Dr. Henrik Svensmark at the Danish National Space Institute has proposed an additional mechanism that cosmic rays seed the formation of low-level clouds by creating ionization tracks that act as nucleation sites for water droplets. If increased cosmic ray flux produces increased cloud cover, that would increase Earth's albedo, the fraction of incoming solar radiation reflected back to space, potentially contributing to a cooling effect. Svensmark's hypothesis, published in Nature Communications in 2017, remains contested in the scientific literature, with some researchers finding support in climate data and others disputing the magnitude of the effect. It is labeled as a hypothesis, not a consensus finding, but it is published, peer-reviewed, and taken seriously enough by climate scientists to be actively investigated. And it adds another potential pathway by which a field minimum could affect global climate, separate from and compounding the direct radiation and ozone effects. The cosmic ray increase is real. It is measured, it is ongoing. Its consequences scale with the field's decline, and at Lachamp's scale field strengths, those consequences move from manageable to potentially civilizational in their scope. But the cosmic ray signal is also the slowest of the signals we have been examining, building over centuries, reaching its maximum consequences on the timescale of the field minimum rather than in the immediate years of its onset. The fastest signal, the one that could deliver operationally significant consequences within years rather than centuries, and that is already operating at the margins of tolerance, involves the very model that the navigation infrastructure of modern civilization depends on. And what happens when that model can no longer keep pace with the field it is trying to describe? On February 4th, 2019, two institutions that do not typically make emergency announcements, NOAA's National Centers for Environmental Information and the British Geological Survey, jointly released an unscheduled update to the World Magnetic Model. The press release was factual, technical, and largely ignored by the mainstream media. It described the update as a response to the magnetic North Pole's accelerating drift, which had caused model errors in high-latitude regions to approach the threshold of operational acceptability ahead of schedule. What it described, in the measured language of scientific agencies that do not use words like crisis, was a navigation crisis in slow motion. The World Magnetic Model has been the operational backbone of global magnetic navigation since its first edition in 1960. It is a mathematical representation of Earth's main magnetic field, the field generated by the core dynamo, expressed as a series of spherical harmonic coefficients that describe the field's direction and intensity at any point on the planet's surface and at altitude. From those coefficients, every device that needs to know the difference between magnetic north and true geographic north, every smartphone compass, every aircraft attitude and heading reference system, every submarine inertial navigation backup, every directional drilling tool in every oil and gas wellbore, derives its declination correction. The model is only as accurate as its mathematical projection of how the field will behave over the 5 years between updates. That projection is based on the field's measured rate and direction of change at the time of the update. It assumes the rate of change will remain within the range of historical variability. For most of the model's 60-year history, that assumption held. The field changed slowly and predictably enough that a 5-year projection remained within the 1-degree declination error threshold, the point at which navigational accuracy begins to degrade below acceptable operational standards across the full update cycle. The 2015 model broke that assumption for the first time in the model's history. The pole's acceleration, driven by Dr. Livermore's iron jet beneath Canada and Siberia, was not in the historical variability range that the 2015 projection assumed. By 2018, the model's error in certain high-latitude regions was closing on the 1-degree threshold, approximately 18 months ahead of schedule. Dr. Kieran Began at the BGS was direct about the trigger. The pole was simply moving faster than the model had projected. The mathematical description of the field was no longer accurate enough to be trusted. Consider what a 1-degree declination error means in practice. For a commercial aircraft on an instrument approach to a runway, flying in poor visibility, dependent on electronic navigation rather than visual reference, heading reference errors of even fractions of a degree map to lateral displacements at the runway threshold. The standard instrument landing system provides guidance accurate to approximately 10 meters laterally at the approach threshold. A 1-degree heading error over a 15-kilometer instrument approach produces a lateral displacement of approximately 260 meters. That is not a minor inaccuracy. That is a different runway. For submarine navigation, the implications are different but equally significant. The U.S. Navy and other naval forces use magnetic anomaly maps, detailed maps of the field's local variations caused by the geological structure of the seafloor, as a navigation reference for inertial navigation systems during periods when GPS is unavailable or untrusted. Those anomaly maps are calibrated against the World Magnetic Model's description of the main field. A model error that drifts over years systematically biases the anomaly navigation solution. Over a 1,000-kilometer transit, A 1-degree declination error accumulates a year of positional uncertainty of approximately 17 kilometers. Dr. Began has confirmed in public statements that the rate of polar acceleration is the primary driver of the emergency update frequency, and that the 2025 scheduled update will again need to address a pole that has continued accelerating since the 2019 emergency release. The directional drilling industry presents a third operational domain where the WMM's accuracy is not an abstraction. Modern oil and gas wells are drilled directionally, horizontally in many cases, for distances of 3 to 5 kilometers from the vertical wellbore. The tools that guide the drill bit use magnetic sensors calibrated against the WMM to maintain the wellbore on its intended trajectory. A declination error of 1 degree at a depth of 3,000 meters and a horizontal distance of 3 kilometers places the wellbore approximately 50 meters from its intended position. In a dense development area where multiple wells are drilled from the same pad, 50 meters of positional error is the difference between staying in the target reservoir and drilling into an adjacent wellbore. A potentially catastrophic outcome called a wellbore collision. The International Association of Oil and Gas Producers maintains the standards for magnetic surveying in directional drilling. Those standards specify the acceptable error budget for wellbore positioning, and the WMM's contribution to that error budget has been tightening as the pole's acceleration has pushed the model toward its tolerance limits between update cycles. Now ask the question that no institutional publication has formally answered. What happens if the pole's acceleration continues to increase? The 2015 model lasted 4 years before requiring an emergency update. The next model, if the acceleration trend continues, may require an even earlier emergency update, or may fail to maintain accuracy for the full period between updates even with annual monitoring. The model infrastructure was designed for a slowly drifting pole. It is being operated against a sprinting one, and the sprint, as of the most recent British Geological Survey assessments, shows no signs of deceleration. The navigation systems are adapting? Barely, at the cost of emergency procedures with no precedent in 60 years of model history. But there is one consequence of the field's continuing decline that cannot be addressed with a software update or a new satellite constellation or an emergency mathematical revision. It is the consequence that shows up in the ice cores at the Lachamp layer, in the DNA of the extinct megafauna, in the nitrate chemistry of Antarctic ice, and it is the one the institutions have been quietest about, not because they are hiding it, but because the compound picture requires looking across disciplines that almost never talk to each other. In the summer of 1985, a team of British Antarctic Survey scientists published a paper in Nature that reported something the atmospheric models of the time said should not exist. Above Halley Research Station in Antarctica, the stratospheric ozone column had declined dramatically, by more than 30% relative to the measurements taken in the 1960s. The ozone hole, as it came to be known, was the consequence of chlorofluorocarbon chemistry. Synthetic compounds released by refrigerants and aerosol propellants that, in the cold stratosphere, catalytically destroyed ozone at rates no natural process could match. The Montreal Protocol of 1987 began the process of eliminating CFCs, and the ozone layer has been slowly recovering since the early 2000s. That story is well known. What is less well known is that ozone chemistry is not only sensitive to industrial chemistry, it is sensitive to particle radiation, specifically to the energetic particles from the sun during major storms and from galactic cosmic rays continuously that penetrate the stratosphere and produce nitrogen oxides through ionization reactions. Those nitrogen oxides catalytically destroy ozone through exactly the same kind of chain reaction that CFCs drive, just through a different chemical pathway. This mechanism is not hypothetical. It is observed. Large solar proton events, the intense particle bursts associated with major solar flares, and coronal mass ejections produce measurable ozone depletion in the polar stratosphere that can last for months. The depletion is localized to the polar regions because the magnetic field's geometry channels solar particles into the polar funnel, concentrating their atmospheric impact there. Now remove the magnetic field, or rather, reduce it to 5% of its current strength for 1,000 years. Dr. Alexandre Fournier at the Institut de Physique du Globe de Paris has modeled the UVB radiation environment at Earth's surface during a Lachamp-scale field minimum, combining the increased cosmic ray flux, the increased solar particle penetration, and the consequent stratospheric chemistry. His modeling suggests that surface UVB flux during the Lachamp minimum may have increased by a factor of 2 to 3 above the pre-excursion baseline, not the 30% increase produced by the Antarctic ozone hole at its worst. A factor of 2 to 3, 200 to 300% of baseline, sustained for centuries. The biological consequences of that UVB increase are not speculative. They are documented in the context of the existing ozone hole, where far smaller UVB increases have produced measurable effects on Antarctic marine ecosystems. Research published in Science in 1992 by Smith and colleagues, studying the waters around Antarctica during the annual ozone hole season, found that even a 10% increase in UVB radiation reduced phytoplankton productivity by approximately 6 to 12% in the affected water column. Phytoplankton are not a marginal component of Earth's biology. They generate approximately 50% of the planet's atmospheric oxygen. They are the base of essentially every marine food web. The fish, the whales, the seabirds, the human fishing industries that feed hundreds of millions of people, all of it sits on top of a foundation of microscopic photosynthetic organisms that are exquisitely sensitive to UVB radiation. A sustained UVB increase of a factor of 2 to 3, maintained for centuries across the global ocean, would not just reduce phytoplankton productivity, it would restructure marine food webs from the bottom up. The terrestrial consequences follow the same logic. Crop sensitivity to UVB radiation has been systematically studied by the United Nations Environment Programme's Environmental Effects Assessment Panel. Their data shows that a UVB increase of 15% reduces soybean yields by approximately 25% and wheat yields by approximately 15%. Those are the numbers for a 15% UVB increase. The Fournier modeling suggests the Lachamp minimum drove a 200 to 300% increase. The agricultural system of modern civilization, which operates on yield margins narrow enough that a 10% global crop failure would produce regional famines, was not designed for a UVB environment of that magnitude. This is the mechanism that Dr. Alan Cooper and Dr. Chris Turney identified in their 2021 science paper as the primary driver of megafauna extinctions during the Lachamp excursion, not direct radiation killing large animals. The dose levels involved are not acutely lethal to large vertebrates, but food chain collapse, the plants stressed by UVB, the productivity of the ecosystems those animals depended on declining, a world that could support the population densities of Pleistocene megafauna across Australia and the Americas simply becoming unable to produce enough biomass to sustain them. Population by population, species by species, the megafauna starved out of existence, not by a single dramatic event, but by a centuries-long degradation of the productive capacity of the ecosystems beneath them. Research published by Traversy and colleagues in 2016 analyzed nitrate concentration spikes in Antarctic ice cores at the stratigraphic layer corresponding to the Lachamp excursion. Nitrate spikes in ice cores are a proxy for atmospheric nitrogen chemistry events, specifically for periods of elevated nitrogen oxide production in the stratosphere from particle radiation. The Traversy analysis found evidence of sustained ozone depletion events lasting years to decades embedded within the broader Lachamp excursion signal. Not a single pulse, a chronic, sustained disruption of stratospheric chemistry over timescales comparable to human lifetimes. That is the full shape of the biological threat from a field minimum. Not dramatic radiation poisoning, not sudden death. A slow, relentless degradation of the atmospheric chemistry that filters the sun's radiation, the ocean chemistry that produces half the planet's oxygen, and the terrestrial productivity that feeds the land ecosystems, operating simultaneously, compounding each other, on timescales that span generations. The question is not whether this can happen. The geological record answers that question unambiguously. It has happened at least once in the last 50,000 years, and the evidence of what it did is preserved in ice cores and in the DNA of extinct species. The question, the one this investigation has been building toward from its first data point, is whether it is happening again. Whether the 10% decline, the sprinting pole, the splitting anomaly, the escalating satellite damage, the disrupted migrations, and the rising cosmic ray flux are the early symptoms of a system moving toward another minimum. And to answer that question honestly, we have to do something that investigation demands and that institutional communication rarely does. We have to sit with the uncertainty, present the competing interpretations fairly, and say plainly what the data does and does not tell us. On November 22, 2013, 3 satellites streaked into low Earth orbit from the Plesetsk Cosmodrome in northwestern Russia, tucked inside a Rocket launch vehicle that deposited them into a precisely calculated orbital configuration spanning altitudes between approximately 430 and 530 kilometers. They were named Alpha, Bravo, and Charlie. Together, they constitute the European Space Agency's SWARM mission, the most sophisticated magnetic field measurement system ever placed in orbit, capable of measuring the field's strength to an accuracy better than 1 nanotesla. Separating the overlapping contributions of the core dynamo, the lithospheric magnetization, the ionospheric currents, and the magnetospheric field with a resolution that no previous instrument had achieved. SWARM has been returning data continuously for 12 years. 12 years of the most precise magnetic field measurements in human history. And yet 12 years of data measured against a system that operates on timescales of thousands to hundreds of thousands of years is what a single frame is to a feature film. The outer core dynamics that drive the field's behavior, the convection patterns in the liquid iron, the jet streams of molten metal, the flux patches at the core mantle boundary evolve on timescales of decades to millennia. The reversals and excursions that the paleomagnetic record documents unfold over centuries to tens of thousands of years. SWARM is watching a story that began long before it arrived and will continue long after any instrument currently in operation has ceased to function. This is not a criticism of SWARM. It is the most important caveat for everything this investigation has documented. The accelerating decline rate, the polar sprint, the SAA's lobe split, these are real, measured, verified phenomena. But we have been watching them for 12 years. We do not know whether the acceleration that SWARM has measured represents a sustained trend or a transient fluctuation on the long time scale of core dynamics. We do not know whether the iron jet beneath Canada is a permanent feature of the core's circulation or a temporary structure that will weaken and shift. We do not know whether the SAA's second lobe will continue deepening or stabilize and remerge with the primary minimum. Dr. Niels Olsen at the Technical University of Denmark, who leads the SWARM science team, has been precise about this uncertainty in published work. The mission's data has transformed our understanding of the field's behavior, but the observational record is short relative to the phenomena under investigation. The models of core dynamics that use SWARM data as their primary constraint are better than any model that preceded them, and they still cannot reliably project the field's behavior more than a few years forward. The pre-SWARM measurement record extends the baseline, but only partially. The global network of magnetic observatories, approximately 170 stations spread across the planet, has been accumulating data since the mid-19th century. For well-instrumented regions, Europe, North America, parts of East Asia, the record extends back 150 to 200 years with reasonable quality. But the Southern Hemisphere, which overlies the core dynamics most directly relevant to the SAA, has historically poor ground station coverage. The ocean floor above the reverse flux patch at the core mantle boundary is the South Atlantic, one of the least instrumented regions of the planet's surface. The anomaly that is arguably the most important magnetic structure on Earth has been measured for most of history from its edges rather than its center. Dr. Kieran Begin at the British Geological Survey has emphasized this gap in published assessments of the WMM's accuracy in the Southern Hemisphere. The model's uncertainty is highest precisely in the region where the most consequential changes are occurring. That is not a conspiracy of concealment. It is the straightforward consequence of building scientific infrastructure in the populated and accessible northern continents, while the most dynamic part of the field's core expression sits under the least accessible ocean. Dr. Kathy Constable at the Scripps Institution of Oceanography has identified a further modeling gap in the paleomagnetic record itself. The resolution of paleomagnetic dating, the precision with which we can assign ages to the field, features locked into ancient sediments and rocks, degrades as you go further back in time. For the Lachamp excursion, which falls within the range of uranium, thorium, and carbon-14 dating, the timeline is relatively well constrained. For older excursions and reversals, the age uncertainty is measured in tens of thousands of years. That means we cannot determine, from the paleomagnetic record alone, whether past accelerations of polar drift and SAA growth were as rapid as what SWARM is currently measuring, or slower. The record that would allow us to calibrate the current situation against precise historical analogs does not exist with the resolution we need. And here's the institutional gap that sits at the center of everything this investigation has documented. The satellite operators, the grid operators, the navigation model managers, the aviation, radiation, and safety authorities, the marine biologists tracking turtle strandings, they are all working within their own institutional frameworks, using their own data streams, managing their own risk assessments. None of them are wrong within their domain. But no governmental or intergovernmental body has published a compound risk assessment that asks, what happens to all of these systems simultaneously under a sustained field minimum, and how do the failures cascade through the interdependencies between them? A review of publications from the United Nations Office for Outer Space Affairs, the International Atomic Energy Agency, the World Meteorological Organization, and the relevant IPCC working groups confirms this gap. Satellites are assessed by satellite operators. Grid vulnerability is assessed by grid operators and occasionally by space weather agencies. Navigation model accuracy is managed by NOAA and BGS. Cosmic ray dosimetry is managed by aviation radiation safety boards. Each silo has its own risk framework. None of them talk to each other about the compound scenario. That is not a conspiracy. It is a failure of institutional imagination. The natural tendency of bureaucratic structures to manage the risks they were designed to manage within the boundaries of the mandate they were given on the timescale their planning horizons can accommodate. The magnetic field's behavior operates on timescales that exceed every planning horizon in every institution currently responsible for managing the infrastructure it threatens. And the compound risk, the simultaneous cascade across satellites, navigation, grids, cosmic rays, ozone, and food systems, has no institutional home. This is where an honest investigation does something that neither institutional communication nor conspiracy content typically does. It presents the competing interpretations of the evidence fairly, completely, and without predetermined conclusion. Not because the truth is unknowable. It is knowable, and future data will constrain it, but because the data we currently have genuinely supports more than one interpretation, and intellectual honesty requires acknowledging that. There are three interpretations of the evidence this investigation has assembled. They are not equally probable in the view of every scientist working in this field, but they are each grounded in the data, each consistent with some portion of the geological record, and each carries its own implications for how the field's behavior over the coming centuries should be understood. The first interpretation is the most benign, and it deserves to be presented first and presented fairly because its supporting evidence is real. The field is in a normal fluctuation. The paleomagnetic record, read carefully, shows not just reversals and excursions, but many periods of rapid field change that did not result in either. The field has weakened rapidly before and recovered. The pole has moved quickly before and slowed. The SAA has expanded and contracted on timescales that the limited historical record has not fully captured. The current 10% decline since 1840, while the largest in the instrumental record, is not unprecedented in the geological record. High-resolution sediment cores from the Azores and the Indian Ocean show the field declining at comparable rates during periods of the Holocene from which it subsequently recovered without approaching excursion thresholds. The supporting evidence for this interpretation is substantive. The current dipole moment, approximately 8 times 10 to the 22nd ampere meters squared, is still roughly twice the value associated with reversal initiation in previous events. Dr. Constable's long-term modeling of field behavior shows that the dipole has fluctuated by 30 to 40% around its mean value over the Holocene without approaching reversal. The current value is below the Holocene mean, but within the range of normal variability. The pole has moved rapidly before, in the paleomagnetic record. The resolution of that record is too coarse to determine how rapidly, but the current speed is not definitively outside the geological range of variability. Under this interpretation, the current field behavior is an episode of elevated variability within a system that fluctuates on centennial timescales. The SAA will stabilize. The pole will slow. The field will recover. The satellites will continue experiencing elevated anomaly rates inside the SAA, and the WMM will require more frequent updates, but the trajectory will not continue indefinitely toward a minimum. The second interpretation occupies the middle ground, and it is the one that a plurality of scientists working on field dynamics currently consider most consistent with the available evidence. The field is in an excursion, a Lachamp scale near reversal, from which it will ultimately recover without completing a full polarity flip. The structural signatures are consistent with this interpretation. The SAA's two-lobe split mirrors pre-excursion patterns in the paleomagnetic record. The polar acceleration is within the range of what sedimentary records suggest preceded the Lachamp excursion, and the rate of dipole decline, if extrapolated at current pace, reaches excursion threshold values within a time frame of centuries to a few millennia. This interpretation does not require the field to complete a reversal. Excursions are more common than full reversals in the paleomagnetic record. The field has approached the reversal threshold and pulled back multiple times for every full flip it has completed. The Lachamp excursion itself is an example. The field collapsed to 5% of its current strength. The poles wandered to equatorial latitudes, and then the field recovered to its pre-excursion polarity. The process was not a reversal. It was a near miss that lasted approximately 4,500 years. Under this interpretation, the consequences for modern infrastructure and biology are serious but bounded. A field minimum lasting hundreds to a few thousand years, with the satellite damage, navigation degradation, grid vulnerability amplification, cosmic ray increase, and biological disruption that this investigation has documented, followed by recovery. Serious. Manageable, perhaps, if the institutional compound risk assessment that currently doesn't exist were developed and acted upon, but not permanent. Dr. Jean-Pierre Vallée at the Institut de Physique du Globe de Paris, whose analysis of reversal precursors spans decades of high-resolution sedimentary work, has noted that the current field state is consistent with the pre-excursion signature, not with the more advanced reversal signature, where the dipole collapse is further along and the multipolar structure is more fully developed. The third interpretation is the most concerning, and it deserves to be stated precisely rather than sensationally, because precision is what distinguishes it from alarmism. The field is in the early stages of a full geomagnetic reversal. The SAA's behavior, the polar acceleration, and the overall dipole decline are not a fluctuation and not an excursion precursor. They are the opening phase of the multipolar transition that precedes a complete polarity flip. Under this interpretation, the field will continue declining over the coming centuries and millennia, pass through the excursion threshold that the second interpretation treats as its endpoint, and ultimately complete a full reversal in which magnetic north and magnetic south swap positions. The timeline for a full reversal, based on the geological record, is not necessarily long. Some reversals in the paleomagnetic record appear to have completed in as few as 1,000 years, a geological eye blink. Others took tens of thousands of years. The data does not reliably constrain how fast the current trajectory, if it is a reversal trajectory, would move. What the data does constrain is the direction. The field, under this interpretation, is moving toward a reversal, not away from one. The supporting evidence for this interpretation includes Dr. Vallet's analysis showing that the current field state, while not yet in the most advanced reversal precursor stage, is within the range of states seen in the final centuries before previous reversals began their terminal decline. Pavon Carrasco and DeSantis' 2020 paper explicitly raised the reversal interpretation as a serious possibility in the peer-reviewed literature, not as a fringe claim, but as one of the scientifically credible interpretations of the SAA's behavior. The iron jet that Dr. Livermore identified beneath Canada and Siberia is consistent with the kind of core flow reorganization that precedes field reversals in dynamo modeling. Under this interpretation, the compound cascade this investigation has documented — satellites, navigation, grids, cosmic rays, ozone, food systems — unfolds not over centuries of field minimum before recovery, but over millennia of transition before stabilization in the opposite polarity. What would distinguish between these three interpretations? The data streams that matter most are the continuing swarm field measurements over the next 10 to 20 years. Specifically, whether the SAA's second lobe continues deepening or stabilizes, and whether the overall dipole decline rate continues accelerating or levels off. Ultra-high resolution sediment cores from the Azores region, which overlie the core structure driving the SAA, could provide paleomagnetic analog data with enough temporal resolution to compare the current trajectory against previous excursions and reversals at the scale of decades rather than millennia. And the behavior of the iron jet beneath Canada, whether it persists, accelerates, or dissipates, will be the most direct indicator of which interpretation the core dynamics are moving toward. Only the data, as it accumulates over the coming years and decades, will determine which interpretation is correct. That is not a failure of the investigation. It is the honest position of science at the frontier of what the evidence currently allows us to say. Strip everything back to the evidence, not the implications, not the projections, not the interpretations, the confirmed, measured, published, reproducible data. Because that data, taken together, is the story. And it is a story that does not require embellishment. What we know with certainty, established by multiple independent measurement systems and confirmed in peer-reviewed literature, Earth's magnetic field has declined by approximately 10% in overall dipole strength since Carl Friedrich Gauss established the first systematic baseline measurement in 1840. The rate of that decline has accelerated. Approximately 8% of the 10% total loss has occurred since 1970. The South Atlantic anomaly, the region of dramatically weakened field centered over Brazil and the South Atlantic, currently covers approximately 30 million square kilometers, with a field strength at its center of approximately 22,000 nanoteslas, less than half the global average. Since approximately 2015, the SAA has developed a second intensity minimum off the southwestern coast of Africa, creating a two-lobe structure confirmed in peer-reviewed literature by Pavon Carrasco and DeSantis in 2020. What we know with certainty about the pole, the magnetic North Pole, has accelerated from a historical drift rate of roughly 0 to 15 kilometers per year through most of the 20th century to its current speed of over 90 kilometers per year. It crossed the international dateline into the Eastern Hemisphere in 2019 for the first time in the instrumental record. The World Magnetic Model required an emergency out-of-cycle update in February of 2019, 1 year ahead of schedule, explicitly triggered by the pole's acceleration. The cause of the acceleration has been identified by Dr. Philip Livermore and colleagues as a high-speed jet of liquid iron at the outer core boundary, published in Nature Geoscience in 2017. What we know with certainty about the consequences already observable: satellite anomaly rates inside the South Atlantic. Anomaly have increased by approximately 30% between 2005 and 2020, consistent with continued field weakening. Surface cosmic ray flux has increased by an estimated 3 to 4% consistent with the field's 10% dipole decline, confirmed by neutron monitor trends at Ulu and McMurdo. Ground-based navigation systems dependent on the world magnetic model are operating at the margins of their designed accuracy envelope in high-latitude regions. Biological magnetoreception systems, documented in sea turtles, whales, migratory birds, and other species, are showing measurable stress responses consistent with the field's current rate of change. Geomagnetically induced current vulnerability in the power grid has increased as the field's ambient strength has declined. What remains genuinely uncertain whether the current trajectory represents a transient fluctuation within normal Holocene variability, a Lachamp scale excursion precursor, or the opening stages of a full geomagnetic reversal. Whether the iron jet beneath Canada will persist, accelerate, or dissipate, whether the SAA's second lobe will continue deepening or stabilize, whether the rate of dipole decline will continue accelerating or plateau. What is unknown and unassessed, the compound infrastructure vulnerability across satellites, navigation, power grids, and food systems under a sustained field minimum. No governmental or intergovernmental institution has published a risk assessment that addresses these systems in combination. Each domain is managed within its own institutional silo, against its own risk framework, on its own planning horizon. The compound risk, the cascading failure scenario that would emerge if all these systems were stressed simultaneously by a sustained field minimum, ZUSU has no institutional home and no formal risk assessment. What this channel will continue watching, the Swarm mission's data releases, which the European Space Agency makes publicly available through its Earth Online data portal. The next scheduled World Magnetic Model update, due in 2025, which will either confirm that the pole's acceleration has continued or provide the first evidence of a potential deceleration. Published analyses of the SAA's second lobe evolution, specifically whether the separation between the two minima is increasing or stabilizing, and the continuing paleomagnetic research from ultra-high resolution sediment cores in the South Atlantic and Azores regions, which represents the best available method for placing the current field behavior in the context of the last several 100,000 years of core dynamics at the temporal resolution needed to distinguish between the three interpretations this investigation has presented. The gap between what the field is doing and what the institutions managing the infrastructure that depends on it have publicly acknowledged is the gap this channel exists to examine. Not because the institutions are lying, not because there is a conspiracy of concealment, but because the compound risk crosses institutional boundaries that were not designed to be crossed, operates on timescales that exceed standard planning horizons, and requires a kind of synthesis across disciplines. Geomagnetism, space weather, power systems engineering, aviation safety, marine biology, atmospheric chemistry that no single agency is mandated or equipped to perform. We are performing it here, and we will continue performing it as the data comes in. There is a specific kind of discomfort that rigorous investigation produces, not the discomfort of conspiracy content, which offers the relief of a named villain and a simple explanation, and not the discomfort of sensationalism, which substitutes dramatic intensity for actual understanding. It is the discomfort of genuine uncertainty about something large, of knowing enough to understand the stakes without knowing enough to predict the outcome, of sitting with an open question that the evidence has sharpened into a genuine investigative tension but has not yet resolved. That is where this investigation stands. The field is weakening. The pole is sprinting. The anomaly is splitting. The satellites are logging damage. The navigational models are straining. The animals are struggling to read a map that is changing faster than they can adapt. The cosmic rays are incrementally flooding through a shield that is incrementally thinner than it was when the measurement began. And the infrastructure of modern civilization, the satellites, the grids, the navigation systems, the food systems, was built entirely during a period of magnetic stability that may or may not continue. None of that is speculation. Every element of that summary is drawn from published, peer-reviewed, independently verified data. The instruments are real. The measurements are real. The trend is real. What remains uncertain is the endpoint, whether the field is fluctuating, approaching an excursion, or beginning a reversal. And that uncertainty is not a reason to dismiss the investigation. It is the investigation. The gap between what we can measure and what we can predict is exactly where the most important work is being done right now, by the scientists whose names have appeared throughout this episode with instruments that did not exist a generation ago. We should address something directly before closing, because this topic attracts a specific kind of content that this channel has no interest in producing. The internet carries regular claims that the pole shift is imminent, that a sudden crustal displacement will reshape the continents within years, that HARPy or some government technology is driving the field's behavior, that the institutions tracking this data are concealing a catastrophic truth. None of that is supported by the physics. Crustal displacement requires a force sufficient to overcome the rotational inertia of the entire lithosphere. No proposed mechanism comes remotely close to providing that force, and the geological record shows no evidence of sudden crustal displacements correlating with field reversals. HARP's maximum radiated power is approximately 3.6 megawatts. The Earth's magnetic dynamo is powered by approximately 10 to the 21st watts of thermal energy from the core. The ratio is approximately 500 trillion to 1. No technology in existence or theoretically conceivable could influence outer core dynamics. And the data, all of it, every swarm measurement, every world magnetic model coefficient, every paleomagnetic paper is publicly available. The European Space Agency publishes swarm data through its Earth Online portal. NOAA publishes the World Magnetic Model coefficients at no cost. The peer-reviewed literature is accessible through any university library, and much of it through Google Scholar directly. The real story does not need a conspiracy. The ordinary physics, honestly examined, is alarming enough without embellishment. A 10% field decline in 180 years. Accelerating. A pole moving 90 kilometers per year with no precedent in the instrumental record. An anomaly the size of a continent splitting into two lobes in real time. These facts, stated plainly without dramatization or conspiratorial framing, are more genuinely unsettling than anything the fringe content produces, because they are real. The actual human fingerprint in this story is not in causing the field's behavior. The liquid iron dynamics of the outer core are not responsive to anything humanity has done or could do. The human fingerprint is in building the infrastructure of modern civilization, the satellites, the power grids, the navigation systems, the food supply chains, during an anomalously stable period of the magnetic field's history, without serious institutional planning for what happens when that stability ends. That is a failure of imagination and horizon planning. It is a story about the mismatch between the timescales on which human institutions operate and the timescales on which the planet operates. And it is a story that is more important, more tractable, and more honest than any conspiracy explanation. The scientists whose work has appeared throughout this episode are not hiding anything. Dr. Began publishes his WMM assessments. Dr. Livermore publishes his core dynamics modeling. Dr. Constable publishes her long-term field behavior work. Dr. Cooper published his megafauna extinction analysis in Science, one of the most visible scientific journals on the planet. The data is public. The uncertainty is acknowledged. The concern is real, and it is in the peer-reviewed literature. What is missing is not transparency. It is synthesis. It is the compound picture that emerges when you read across all of those publications. From geomagnetism to space weather, to power systems, engineering, to marine biology, to atmospheric chemistry, and ask what they are collectively saying about the resilience of the systems that 7 billion people depend on. That synthesis is what this channel does. It is what this community demands. And it is what we will continue delivering as long as the data keeps coming in and the open questions remain open. The swarm satellites are overhead right now, completing another orbit, measuring the field to better than 1 nanotesla, adding another 94 minutes of data to the archive that is slowly, carefully, building the picture of what the outer core is doing 3,000 kilometers beneath the ground you are standing on. The data will accumulate, the models will improve, the uncertainty will narrow, and when it does, when the next decade of measurements makes the three interpretations distinguishable, when the SAA's second lobe either deepens past the point of ambiguity or stabilizes into something manageable, when the pole either continues its sprint or shows its first signs of deceleration, Signal Watch will be here. We will be watching, we will be reading the papers, we will be in the data, and we will bring you the full picture, without conspiracy, without sensationalism, and without the comfortable reassurance of telling you that everything is fine when the evidence has not yet earned that conclusion. The field is doing something, the instruments are watching, and so are we.